In this video, we continue our study of linear dynamical systems, that is to say, the behavior of the powers of a bounded linear operator. In previous videos, we've seen that when this operator happens to be a contraction on a reflexive Banach space, then the system is ergodic in the sense that the Cesaro averages of the power do converge in the strong operator topology, that is to say, acting on any vector in the Banach space, to the projection of that vector onto the null space of identity minus t. Now, in this video and the next one, we look at a stronger form of ergodicity called mixing, and you can have a look at it on property 2 of theorem 14.8. What this property is telling us is that the system has its Cesaro averages converging in the strong operator topology, but not just for the powers themselves, but for any subsequence of the powers. Now, if you think about what this property means, especially in somewhat concrete applications, it seems very strong, because if you have a system that, let's say, go back to the value it started from, or close to the value it started from infinitely many times, but very rarely, say once in every block of time between 2 to the n and 2 to the n plus 1, then the Cesaro averages won't pick that up, right? If that vector is in the range of identity minus t, say the Cesaro averages will converge to 0, even if you do go back to the original value x infinitely often, but just rarely. Whereas this property completely rules that out, right? Because you can, if you were to go back close to where you started infinitely many times, you could pick precisely the sequence of those times for which you go back closer to where you started, and the Cesaro averages of that will be essentially constant, and they certainly wouldn't go to 0 unless you start with 0, obviously. Now, this very strong property of the dynamical system won't hold for every h and every contraction t, but it will hold, and that's the content of the two theorems we are going to prove about mixing system, whenever the orbits themselves, the powers of the operator applied to the vector h, go to 0 in the weak operator topology. So the first theorem we're going to prove, theorem 14.8 in this video, due to Blum-Hanson in 1960, it's a theorem in Hilbert spaces for contractions, just like the von Neumann theorem. It's not a very interesting theorem on the null space, because on the null space, all the powers of t are just the identity. But if you're on the closure of the range, what this theorem tells you is that this convergence of the Cesaro averages over any subsequence is equivalent to the weak convergence of the orbits themselves. So it's a Tauberian theorem in nature. It trades one sort of convergence for another sort of convergence. And one is in a sense stronger than 2 because it involves the powers rather than some convex combination of the powers, but it is much weaker than 2 because it's in the weak topology as opposed to being in the strong topology. And the content of the theorem is that these two modes of convergence are equivalent. Now, if it happens for every h, then we say that the system is mixing, but this Tauberian property, the equivalence of 1 and 2, you can look at it orbits by orbits, and you could have a system for which this is true for certain h and not true for all h. So we'll prove this theorem of Blum-Hanson in this video. This is typically something that we can do in Hilbert spaces using all of the tools of Hilbert space theory at our disposal, and then we'll ask the typical question we've been asking in this course. Looking at this proof of a theorem in Hilbert spaces that involves weak convergence and convex combination and strong convergence, can I maybe extend that to general reflexive Banach spaces using the techniques that we've learned? And the answer, contrary to the extension of the von Neumann theorem into the von Neumann-Lucida theorem, is, well, we don't know. We absolutely don't know whether or not Blum-Hanson theorem is true in every reflexive Banach spaces. What we do know as of 2007, and a theorem of Müller and Tominov, is that in specific reflexive spaces, such as the spaces of sequences little lp, then the theorem do hold. But it's still very much an open question whether or not this holds in general reflexive Banach spaces, or even whether or not it holds in general in LP of 0, 1, capital LP of 0, 1. So If you want to start doing some research, here's a question you could ask yourself. Can you extend Blum-Hanson theorem to capital LP? If you add the assumption of positivity, just like we did in the Birkhoff theorem, then the answer is yes. But if you do not add this assumption, then we don't know if the answer is yes or if the answer is no. Now, in this video, we'll prove theorem 14.8, see how the proof works in Hilbert spaces, really have a good look at it, trying to find out what is specific to Hilbert spaces in our proof, and then in the last video, we'll prove Müller-Tomiloff extension of Blum-Hanson theorem to little p. Okay, so let's start with the easy direction, which is 2 implies 1, and let's do that by contrapositive. So assume that 1 does not hold, that is to say that T and H does not converge weakly to 0. As n goes to infinity. Now what does that mean? That means that there exists an epsilon, and there exists a g in the unit sphere of H, and there exists a subsequence nj, well, an increasing sequence of natural numbers in a subsequence of the powers, such that Tnj of H tested on G stays above epsilon for all j in n. Okay, pick such a sequence where you stay away from 0, which you can if you're not converging weakly to 0. Now, what happens when I look at the Cesaro averages along that particular subsequence of H? Well, I'm taking a norm. So a norm is a supremum of these vectors tested on elements of the unit sphere of the dual, which in the case of a Hilbert space can be identified with the space itself. So this is certainly greater than 1 upon n, sum j equal 1 to n, Tnjh tested on G, because G is just one of those vectors. Now, once it's tested on G, every Tnjh tested on G is greater than epsilon, so this entire thing is greater than 1 upon n, sum j equal 1 to n of epsilon, which is equal to epsilon, and that's for every n, so this can now possibly go to 0. Okay, so that proves the easy part. 2 implies 1. Now, what about 1 implies 2? So for 1 implies 2, let's denote by alpha the limit of the Tn to the h, the norm of the Tn to the h as n goes to infinity. Now this limit has to exist because the sequence T and h is non-increasing. That's because T is a contraction. So this limit here is really an infimum, right, or lim-inf if you want. So this exists, and this may or may not be 0. Now, if it is 0, okay, if it is 0, then I can look far enough in any subsequence. So if alpha equals 0 and nj is an increasing sequence of natural number, then what have we got? Then we've got that there exists a capital J such that above that capital J, Tnj of H is smaller than epsilon. So for every epsilon there exists a J such that this holds. But now what does that give me? I mean, that gives me that for every n in n, if n is greater than that J, so for every epsilon there exists a J such that for all n greater than J, what do we get? We get that 1 upon n sum of the Tnj, and notice that this sequence nj was chosen to be arbitrary and independent of epsilon, or independent of capital J, more importantly. So this here, what can I say about it? I can say this is smaller than 1 upon n sum j equal 1 to capital J of my Tnj of H, plus 1 upon n sum j equal capital J plus 1 to n of Tnj of H, just by triangle inequality. Now the first term, again by triangle inequality, is smaller than j divided by capital N times the norm of H, because Tnj is a contraction, And then the second term, well, the second term is smaller than epsilon because t and j of h is smaller than epsilon for all j greater than capital J. So this entire thing will tend to epsilon as capital N goes to infinity. So for every epsilon, the limit of 1 upon n sum j equal 1 to n of t and j h, or the lim sup, let's say, of that as n goes to infinity is smaller than epsilon. And so, okay, so this converges to 0 in the norm topology. Right, so if alpha equals 0, we are done. Now, what happens if alpha is not 0? So that was alpha equals 0. So if alpha is non-zero, then without loss of generality, I can take alpha to be 1. Because, okay, if alpha is not 1, if not, I can replace h by h divided by alpha, and that is still an element of the range. Okay, so I've got my alpha equal to 1, and I'm going to have to show the convergence of the Cesar averages of subsequences. Let's see how that goes. So for the main part of the proof, we are in the situation where Tn of h in norm tends to 1 as n goes to infinity, and Tn of h goes weakly to 0. Okay, so if we are in such a situation, and we give ourselves an epsilon, we can certainly pick a capital M, such that for all little m above capital M, Tm of h is smaller than 1 plus epsilon. Actually, let's do that with a square. Tm of h square is smaller than 1 plus epsilon. Okay, this is possible because we have the convergence of the norm to 1. Now, in the meantime, we have the weak convergence to 0. So how do we exploit that? We're going to pick a k in n such that for all k greater than capital K, when I look at the dot product of t capital M plus k of h tested on t capital M of h, I want that to be smaller than epsilon. That's possible by 2. I fixed my capital M here, and then I look at this element of the dual, and then if I take an element in my sequence that is sufficiently far, for an m plus k that's sufficiently large, then this dot product has to be small because the sequence of powers applied to h converge weakly to 0. Now, if I stare at this, this is an almost orthogonality statement. It tells me that if I look far enough in my sequence, then all of the elements will be almost orthogonal to that fixed element Tm of h. By almost, I mean they will be maybe not have an inner product 0, but have an inner product small. Now, the first thing we're going to do is improve that to a stronger statement about almost orthogonality in the orbits. So we're going to give ourselves an n and an m in n, and we're going to say that our m is far enough and that our n is even further by at least capital K. And then we're going to look at Tn of h applied to Tm of h. Okay, and I want to see that as the cross term in the expansion of a square, so I'm going to put a 2, and I see that as Tnh plus Tmh squared minus Tnh squared minus Tmh squared. Now remember that the infimum of the values of this norm is 1, right? This limit here is actually an infimum because I have a contraction, so this norm decreases or do not increase with n. Okay, so that is to say that this thing here is some number above 1 and this is some number above 1, so I'm subtracting at least 2. So this is smaller than Tn of h plus Tm of h squared minus 2. Okay, since the infimum of the Tnh is 1, that's by definition my alpha. Okay, that we've normalized to be 1. Now in here, what I want to do is I want to factor out, what is it, t little m minus capital M. And then I get that times T capital M of H plus Tn minus little m plus capital M of H. Right, now this is still a contraction, so this is smaller than the norm of T capital M of H plus the norm of Tn minus m plus capital M of H squared minus 2. And then let's expand that square. We get Tm H squared plus Tn minus m, which is some number above k, plus capital M of H. And then we get the cross terms. And then we get minus 2. Now, we have these two assumptions here, assumption 1 and assumption 2. Well, not assumption, but consequences of the situation we're in, because we've already treated all of the other cases before. And so in this situation, we know that this first term is smaller than 1 plus epsilon, and so is the second. So we have 2 times 1 plus epsilon minus 2 plus 2 times this cross term, but this cross term we know by 2 that it is smaller than epsilon. So you put all of these things together and you get 2 minus 2 plus 2 epsilon plus 2 epsilon. So this is 4 epsilon. Okay, so we've shown that these dot products here are all small if you take both m and n far enough, and you take n minus m sufficiently apart from each other. So if you look far enough in the sequence of powers and you look at elements that are far enough apart, then they are just trying to get orthogonal to each other. They're close to being orthogonal to each other. And that's fundamentally the idea that we are trying to exploit here. So how do we exploit it? Well, let's take a subsequence. So let's consider Nj a sequence of natural number that is increasing. Okay, and now let's take a capital N in N, and let's have a look at the Cesaro averages that we are interested in. Okay, what can I say about those? Let's square them, and let's just expand that square. So first of all, on the diagonal, when j is equal to k, things are pretty easy. I can just say 1 upon n squared, sum j equal 1 to capital N of norm of t and j of h squared. And then I have the terms of the diagonal, and I'm going to rewrite them as 2 divided by n squared, sum j equal 1 to n, and sum k equal j plus 1 to n of t and j h, t, and k, h by symmetry. Now, the first term here is really smaller than 1 upon n times the norm of h squared. So that's certainly going to go to 0 as capital N goes to infinity. And then I have the second term to deal with. 2 upon n squared, sum j equal 1 to capital N, and the sum from k equal j plus 1 to n of the t and j h, t and k of h. Okay, so what happens here? So this term here that involves this dot product, I know that they are small whenever I'm far enough in the sequence n and j and nk are far enough apart. So let's try to exploit that. When I look at the sum from j equal 1 to n of the sum from k equal j plus 1 to n, okay, I need to stop my sum here at n minus 1, because if not, there's a problem when I take j plus 1. Yeah, that's what it is. So when I look at this, what do I get? I can look at various terms. I can look at the term, first of all, when nj is between 0 and capital M. So if nj is in this region, I have at most capital M terms in j. right? Because nj is a subsequence of the naturals. So this is certainly smaller than capital M divided, if I have my divided by n squared times the number of terms in k, which is n, times what I have here in this dot product, which is certainly controlled by h squared. So this would go to 0 as n goes to infinity. So that's the way I handle the part of this cross terms whenever nj is small enough. And capital M is fixed, nothing to do with capital N. Now what do I do if nj is above capital N? Well, that's where I want to start exploiting my almost orthogonality. So now I have a term where j is above capital M, nj, and let's say my nk is far enough for my nj, so it is at least nj plus k. Now in that situation, I know that my inner products by almost orthogonality are all smaller than epsilon. So this here is smaller than epsilon divided by n squared, and then in those sums I've got at most n terms in each. I've got fewer than that for that matter, but this is smaller than epsilon times n squared divided by n squared. Oh, sorry, that wasn't epsilon, that was 2 epsilon. Okay, but the point is this is smaller than 2 epsilon for all n. Right, and now what else can I do? What else do I have to do? I have to look at what happens when I'm in this set with my nj, but I'm not in that set with my nk. So that last term that I need to look at is when I have sum j equal 1 to n minus 1, sum k equal j plus 1 to n, my nj is far enough, and nk is now close to nj. So nk is, well, it has to be above nj because k is above j, but it is between nj plus 1 and nj plus k. Now, in that context, in k, well, there cannot be more than capital K term doing that, because I need all of this term in an interval of natural numbers, all of these terms in an interval of natural numbers that has only k element. This is fewer than k elements for that matter. So this is certainly smaller than 1 upon n squared, the number of term in the j sum, which is n, and the number of term in the k sum, which is k, times norm of h squared. So again, this is k norm of h squared divided by n. K has been fixed a long time ago, independent of n, so this goes to 0 as capital N goes to infinity. So putting all of these things together, what have we proven? We have shown that the limit as capital N goes to infinity of 1 upon n sum of t and j equal 1 to capital N of h in norm is smaller than 2 epsilon. Okay, and epsilon was arbitrary, right? It was fixed, again, quite a while back, all the way over here. We fixed an epsilon, and then we picked an m, and we picked a k. And now our capital N is independent of any of that. When we send it to infinity here and there, okay, that depended on capital M and capital N, but now this has disappeared as I've taken the limit, and I have a limit that is smaller than 2 epsilon for every epsilon. And that proves the theorem. That proves that 1 upon n sum j equal 1 to capital N of t and j of h goes to 0 as capital N goes to infinity. Okay, that is the proof of Blum-Hanson theorem. Now, looking at this proof, what is the idea behind it? Well, the idea behind it is really what we've exploited here. It's the idea of the powers of the sequence trying to get apart from each other, trying to get orthogonal after a while, and if you take them sufficiently far apart. Now, obviously, we don't have orthogonality in Banach spaces, So we will need in a more general situation to have an analog of that idea of this orbit wandering in a direction that is reasonably orthogonal to the other orbit when you look. Here is the picture maybe that one should have in mind when you look far enough in the sequence. So you have your capital M here, and then you look sufficiently far away, and the point you've reached here compared to the point you reach there will be in close to orthogonal directions. So this is the idea that we're going to have to mimic in order to prove the theorem in a more general situation. We will do that in the last video.